In this video, we will go over some intermolecular forces. Basically, the three intermolecular forces that we should concern ourselves with are hydrogen bonding, polar-polar interactions, that is also known as dipole-dipole interactions, and then dispersion forces. There's also another one called ion water or ion solvation interactions. That is when an ionic compound interacts with water, and water will solvate it. That is, the water molecule will surround the sodium ions and the water molecule will surround the chloride ions. That's a full charge of an ion interacting with the partial charge of the polar water molecule. So the answer to part D in 1110 is this is an ion solvent or ion water interaction if we were to dissolve this in water. Now benzene would only have dispersion. Dispersion basically for hydrocarbons, even though this forms a ring, hydrocarbons really cannot interact with one another through any of these special types of bonds. So there's nothing partial positive, partial negative. It's a fully nonpolar molecule. So a benzene will interact with another benzene through dispersion forces. You also want to remember like dissolves like. Polar goes with polar, nonpolar goes with nonpolar. Now, CH3Cl is a polar molecule. The Cl actually pulls. So if we were to draw the structure of CH3Cl, this is called methyl chloride. So phosphorus is happy at 5. Phosphorus is happy at 5. Fluorine is happy at 3. Fluorine is happy at 7, but there's 3 of these. So we have 21. So we need to get 26 valence electrons around the PF3 molecule. So we need to get 26 valence electrons across the PF3 molecule. So we'll make phosphorus our central atom. We'll have our 3 fluorines. So for 26, remember halogens 1, 2, 3, 4, 5, 6 are happy at 7. So 7, 1, 2, 3, 4, 5, 6, 7, 8 fulfills the octet rule. 1, 2, 3, 4, 5, 6, 7, 8 fulfills the octet rule. 1, 2, 3, 4, 5, 6, 7, 8 fulfills the octet rule. But we need to get 26 valence electrons. So counting this all out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and 26. So that lone pair of electrons makes this molecule polar. Because it's polar, we would expect PF3 to bind to another PF3 via dipole-dipole interactions. So finally, we already talked about NaCl being an ionic compound. Basically, if you dissolve it in water, you'll get solvation. Other than that, NaCl will interact with one another through ionic interactions. And CS2, if you look at the symmetry of the molecule, is nonpolar. So it would be held together with another CS2 carbon disulfide with dispersion. So the net effect here is we have dispersion, polar-polar or dipole-dipole interactions, dipole-dipole interactions, ionic interactions, and then dispersion. Okay, nonpolar molecule. Another intermolecular force is hydrogen bonding amongst themselves or hydrogen bonding with another molecule, 2 different molecules. Here we're looking for a couple of important aspects. We're looking for an OH, we're looking for an NH in the molecule, or we're looking for a fluorine in the molecule. So if you see OH, NH, or F, you can probably think that there's some sort of hydrogen bonding going on here. So looking at these options, C2H6 is benzene. That's a that's a nonpolar molecule. So it's held together by dispersion. HI is an ionic compound, electronegative acid. KF is an ionic compound. Even though there's an F in here, there's no H's in the molecule. So a hydrogen bond must have an H somewhere. BeH2 is a nonpolar molecule. Really, amongst all of these, the only one that could really hydrogen bond is this carboxylic acid, CH3COOH. And this is called acetic acid, by the way. And that OH can hydrogen bond with another OH from another acetic acid. Finally, hydrogen bonding has a profound effect on boiling points. So the boiling point of this molecule here, known as 1-butanol, is 117 degrees C, while this one here, the ether, is 34.5 degrees C. So why is this 117 versus 34.5? when they have the same number of carbons, same number of hydrogen, and the same lone one oxygen. The arrangement such that you have that OH. Okay, hydrogen bonding, OH hydrogen bonds with another H in a second molecule. The NH hydrogen bonds with another H in another molecule, or the F can hydrogen bond with an H of another molecule. So it could be the same molecule or it could be a totally different molecule. So the reason for the discrepancy in this high boiling point takes a lot to boil butanol because all of that heat energy is going to disrupt the hydrogen bonds one butanol makes with another molecule of butanol. We see this in hydrogen bonding with a lot of liquids. The most famous example is water. And also we see this now with the alcohols. 1-butanol is an example of hydrogen bonding, giving rise to a very large boiling point.